Okay, hello everybody. Am I coming in loud and clear? Can you hear me out there? Let me know on the chat. Hello, Abdul Rahman, Zhonghua, Maximilian. Hello. Todd, hello. So, welcome back. It's nice to have you here. I have been asking a poll of students, can you believe that it is week 9, the end of week 9? Oh my goodness. 5 people said yes, 6 people said no, 11 people said, shh, I'm sleeping, professor, and 2 people said, I stopped learning in week 2, bruh. Anyway, whatever is happening here, I hope you are enjoying Friday. So this is the final calculus lecture for Fridays. Next week, there might be something happening on Friday, but just watch this space. But this is the final Friday lecture for calculus. All right, so in this class, we are going to look at the exponential function. Last time we looked at the logarithm function and we defined it via an integral, and we're going to build on that today. Okay, so you should have, let me go back to my document camera. You should have these notes, and the topic is the exponential function. Now, many of you will remember this kind of function here, right? Where e is a very special number and x is the variable in the exponent, and it sort of looks a bit like this, right? And this is the number 1, and this is a very special function. So what we're going to do, we're going to play around with that today. Like a lot of things in this course, some things may be familiar from high school or previous studies, and other things will be a little new to you, okay? So some things will be familiar and some things will probably be new, okay? So we're going to introduce the exponential function in interesting ways, look at its properties, do lots of examples, and do some challenging ideas. Now, some of these things will be familiar. This might be new, okay? We're going to use things like L'Hopital's rule and a few other things in here. All right, so let's just refresh our memories from the previous lecture, right? So in the previous lecture, we introduced this logarithm function. And we introduced the following definition. Okay, so you can think of this as, you know, you've got 1 on t, and say here's 1, and maybe here might be x. This area underneath is the value of the logarithm function, okay? So if x equals 2, the area under here would be, you know, log 2, okay? So today we are going to look at this exponential function. Now, exponential functions are really cool, and you see them in English. You know, they talk about population growth growing exponentially, or you know, other things growing exponentially. So there's a lot of interesting applications of the exponential growth. And now, one thing that we can do with the logarithm function, so the logarithm function looks a bit like this, okay? It's an increasing function, right? And so what we can do is invert it, okay? So this is like the line y equals x here. So I know that's an increasing function, therefore it's 1-to-1, and it must have an inverse. So if we reflect that in the line, it looks something like this. So our exponential function is just basically the logarithm function reflected in the line y equals x. Okay, so reflect log x. Okay, so that's a really rough way of introducing the exponential function, but it's fine for our purposes. Let's get into these exponential functions a little bit deeper and see where we go. Okay, what is this magic number e, and what are the other properties of it, right? So we can talk about sort of general exponential functions, and like they're of this kind of um, uh, uh, form. So you might have 2 to the x, or 3 to the x, or 1/2 to the x. Okay, so the a value is called the base, and the variable is called the exponent. Okay, you might have, I don't know, 6 to the power x or something like that. Okay, so these are all examples of basic exponential functions. Okay, so if I just draw, if I bring up GeoGebra, did somebody say GeoGebra? Let's have a look at what these things look like. Okay. Yep. So if I plot my graph of a to the x, watch what happens. So you can see that as the base is between sort of 1 and 5, it increases as we move from left to right. But as the base goes between 0 and 1, you can see here, you can see the value of the base here is 0.73. The graph is actually falling from left to right. Okay. And if it's about 1, well, this isn't quite 1, but it's a horizontal line. Okay. So these are all some of the basic shapes for exponential functions. Okay, pretty cool, right? So if I just pause that, let's have a look at, I don't know, 2 to the x, right? That's a simple one. 1 to the x is just a horizontal line. 1/2 to the x looks like that. So you can see as we move from left to right, the blue curve's increasing, the orange curve's decreasing, and the grey curve is just staying the same. So there are some basic exponential curves, right? Now what we're going to do now is kind of derive this magic number e, okay? It is a bit of a magic number like pi or the square root of 2, and I'll give you some ideas of where it comes from. It's a sort of a magic number. So, okay, we're going to choose a very special value for this base. Not 2, not 3, not 1/2, not 6, such that the derivative of this function at x equals 0 is 1. Okay, so what we're going to try to do is determine a value for the base such that when you differentiate it, you just get the same function. Okay, and this also holds. Okay, so how do we do that? Well, let me show you on the graph again. There are different ways of doing this, but let me show you. Okay, so go back to GeoGebra. Okay, so you can see here, this is like the line y equals x plus 1, and when x equals 0, I mean, this has slope equal to 1, right? So we want this to be sort of a tangent line to our curve. Okay, so if I go back to this thing, you can see, well, that kind of looks like a tangent curve. But if I sort of move it a bit more that way, that's actually a really, I'm getting pretty precise there now. Okay, so whereas if I move it like that, it's no longer a tangent. They're no longer tangent at x equals 0. Okay, but if I go to about 2.7, 2.8, it's really close. Okay, now if I put that one in there and remove this one, you can see actually it's got the right shape. This is exactly a tangent line at the point x equals 0. Okay, so this magic number E is somewhere between 2.7 and 2.8. Okay, so let's dig a little deeper. Well, how do we determine it? You can determine it a few ways. The picture's helpful, no doubt, but in calculus, it comes down to looking at this basic limit, okay? And we get a crazy number that is an irrational number. Okay, it goes on, it doesn't terminate, and it doesn't repeat. And this is actually the number that gives you this and this, okay? Now, there are other ways of coming up with this number. These are a few. But we can actually use what we've learned already in the last lecture to come up with another definition of E. So you can also add to this it's the unique number such that, ST stands for such that, okay, so the integral from, this is like 1 to x usually, but we want a definite value here. So if I draw in my curve, this is 1 on t, right? And if I integrate from 1 up to this magic number E, the area under that curve is 1 unit. Okay. Now E is a bit bigger than 2, and it's a bit less than 3. Okay, so it's about 2.7183. Okay, so there's a couple of ways of doing these sorts of derivations, if you like, of this magic number E. But this is nice because it sort of ties it in with something that involves area and something that we've already looked at before. Okay, so how good is it? It's a magic number. E is a magic number. So you might not have seen this before, but it's really cool, right? You've probably used and worked with the exponential function before, and these properties will probably be familiar, I suspect, but you may not have seen this kind of derivation before. Okay, so yeah, it's really cool, really cool. All right, so what do we see with our logarithm and our exponential function? Well, I am glad you asked. So let me just put them back up on the screen, and I'll just go back to GeoGebra. Okay, so you can see the dark blue curve is the logarithm function, and the light blue curve is the purple curve is either the x function, and we've reflected it in the line y equals x. They're inverses. So okay, so we can make some information about domain and range. If you look at the domain of the logarithm function, it's x greater than 0. That means the range of the exponential function is just, it's got to be positive, right? Okay. And the range of the logarithm function goes from negative infinity to positive infinity. And so the domain for the exponential function is the same. Okay, so I think this should be negative infinity. Okay, so this should be a negative infinity here. So let me just, I've just found a little typo. So let me show you that. Okay, so that should be negative infinity, not 0. All right, so the properties, you know, these things are the inverses of each other. If I differentiate the exponential function, I get the exponential function. If I differentiate e to a function, I can use the chain rule. Okay, so you differentiate the exponent function and bring it to the front and don't change it. If I integrate the exponential function, I get the exponential function plus a constant. And this is just a variation again. It's just the chain rule. Okay, and there's basic exponent laws. So these are things, I guess, that you'd be pretty familiar with. You kind of use these in high school calculus and things like this. So as a basic example, if I'm differentiating, I don't know, e to the x squared, right? This is like this form here. Well, x squared is the exponent function. Differentiate it and bring it to the front. So it will be 2x e to the x squared. Okay, so that's a really basic example of applying this general theorem or general identity. Okay, what about this one? Well, if I'm integrating, what have I got? E to the 2x plus 3. Okay, well, I divide by this coefficient and keep everything the same. Okay, so you can sort of do those directly, or you can invoke the chain rule if you want to. Okay, if you want to. All right. So let's have a look at some special examples. Is there anything that people would like to go through again about any of this part of the lesson so far? Just let me know in the chat, or you can also turn your microphones on. There's only 39 people here today, so let me know if there's anything that's unclear or you'd like me to talk about a bit more in detail. Okay. All right, so here's 3 questions. Evaluate or solve the following. Okay, so let's do the easy one first, right? 3 to the x equals 27. Oh, that's good, Madhav. I'm glad things are clear for you. So let's do this one first. Who can tell me on the chat what is x in this question? If I'm solving the middle one first, yeah, Abdul Rahman, it's pretty easy, right? So 3 to the x equals 27. And 27 is 3 cubed. Okay, so going by this property, x must equal 3. Okay, so that's not a hard one at all, right? But you can also do it another way. You can say, right, 3 to the x equals 27. I'm going to take the logarithms of both sides. And what that means is it's x equal logarithm of 27 to base 3. Okay, so this and this are equivalent. Okay, and so what I can do now, if I really want to, I can just simplify my logarithm. So 27 is 3 to the power 3. Okay, so the 3 can come to the front using log laws. Log 3 to base 3 is just 1. Okay, so that's the long way to get there. This is the very short way to get there. But this really is kind of high school. That's really a high school kind of problem. So I wouldn't spend too much time on that. Let's look at the calculus parts. Okay. So let's call this I. So the integral of e to the 2x, let's apply the fundamental theorem of calculus. And it's going to be this. This is a primitive or an antiderivative. Okay. So I substitute in here and here. All right. And I guess with this one, you could just calculate this, but I think from a precision point of view, what you can do is use the log properties to simplify this in some way, right? So what I might do is I might put that 2 up there, and then e and log cancel each other out. So you actually get a nice expression. Okay. Okay, so we've got e to the natural log, e to the natural log. That cancels out. So we'll get 4 squared there. And 3 squared there. Okay, so that's going to be 8. That's going to be 9 over 2. And so I think we get something like 7 on 2 here. Okay, so I'm just using basic properties of logarithms, exponents, and inverses there. Okay, Carl, question. Y is 1/2 times x. Okay, Carl, do you want to turn your microphone on and ask a question? I'm not quite sure what you're asking.
Oh, hi, sir.
Hi, Carl. How you doing, buddy?
Yeah, I'm great. That I have questions about the first equation that y is it's that one. I'm confused about that. How?
Oh, so
Use
yeah,
yeah.
yep. So it's a good question. So you can see over here, right? So if you have e to like a linear function, you just divide by the coefficient of x, right? So if you differentiate this, you'll get this,
Oh, so it's
okay?
like the chain rules.
Yeah,
Oh,
exactly. So
get it.
I haven't done the chain rule because it's a lot more work,
Yeah.
but that's the idea. You could say let u equal 2x and then do the chain rule,
Oh, yeah, I got
or
it.
integrate by substitution. Yeah, let u equal 2x and integrate by substitution. Yeah,
Okay, yeah. Thank you, sir.
awesome, Carl. Thanks for speaking up.
Yeah, cool.
Okay, so that's that one. That's that one. Let's talk about the third one. Now, who can tell me what strategy would you use to differentiate this? Who can tell me? Product rule. It's the product of two functions. Yeah, absolutely, Carl and Abdul Rahman. Thank you. So, you might want to, let this be u and that be v, and so u dash is going to be 2x, v dash is going to be 3 times e to the 3x. Okay, so pretty easy so far. So it's that times that plus that times that. So it'll be 3x squared e to the 3x plus that times that. And if you want to, you can factorize. Okay. Okay. So these are sort of standard entry level examples. And yeah, I mean, obviously this one's pretty easy. This one's pretty easy, and this one's pretty easy, right? But let's actually go to some more difficult ones, because some of these calculations and some of the problems are not straightforward at all. Okay, so let's move over to a different one. Okay, so this is where it gets harder. Okay, so differentiate 6 to the x. Okay, so what some people do is they think this, right? They go, oh, this is true. So if I differentiate that, I get 6x. Not true. But hang on, get a different pen. That's a 6. Oh, okay. So if you differentiate an exponential with a different base from e, this is not true. Okay, this is not true. And lots of students make that mistake. Yeah, Abdul Rahman, yeah, you're on the right track. You can see it down here. But let's do this by first sort of principles in some sense. And I'll show you how to do it. So let y equal 6x, 6 to the x. We're going to use an idea called logarithmic differentiation. Okay? That's right, Steve. That's why e is a magic number. So if I take the logarithm of both sides, the natural log, I'll get this. Okay? So I've just basically taken the natural log of both sides. Okay? Now, using the logarithm laws, the power comes to the front. Okay? So what I'm going to do, I'm going to differentiate both sides of this with respect to x. It's easy to differentiate this. It'll just be natural log of 6. This one, we use the chain rule. Okay? All right, so I differentiate this with respect to x. I use the chain rule, right? So over here, I'm going to use the chain rule. Okay, what is the derivative of this? Natural log of 6, because the x disappears. Okay. So what is dy dx? Well, let's rearrange and find out. This is going to be 1 on y. Okay, move the y up there and you've got dy dx. Remember, y is 6 to the x. Okay. Okay, so there you go. It's not what you would expect it to be if you just concentrate on this. The derivative of 6 to the x is not 6 to the x. Okay, it's 6 to the x times a special constant. Okay, and the reason why this is true is because log e to base e is 1. Okay, so this kind of idea and the method also works for general exponential functions. So you get something like this. The derivative of this is this. The integral of this is this. Okay. So for example, if I was differentiating 3 to the x, it will be 3 to the x times the natural logarithm of 3. If I'm integrating 2 to the x, it'll be 1 on natural log of 2 times 2 to the x plus a constant. Okay, so that's one of the biggest mistakes that students make when they're given something like this. Okay, they go, oh, this is true, so therefore the derivative must be the same. That's wrong. Okay, don't do that. Yeah, my dog agrees. Okay, so the really important examples. All right, any questions for that example? Because that's quite, like, these things are very, very important. Okay, very, very important. So let me know if there's questions on the chat, or you can turn your microphone on if you need to. Okay, so based on that, let's do a couple of easy examples, right? So we don't even need to do any working for this. We can just say, right, the derivative of 100 to the x is just going to be 100 to the x times the natural log of 100. Okay, and the integral of 5 to the x is going to be 1 on the natural log of 5 times 5 to the x plus a constant. So you can see these examples are pretty easy. So let's make it a bit more challenging. Okay, so I've got 2 more examples to go, and yeah, like, they're a bit crazy. So let me show you. Differentiate x to the power x. It's a bit crazy, right? X to the x, what does that even mean? So now we've got a variable in the base and a variable in the exponent. Oh my goodness, what is going on? Okay, so let me share GeoGebra with you and see what GeoGebra thinks about it. Okay, so I'm going to just put in x to the x here. X to the x. All right, so excellent. Now, a question on the chat. What is 0 to the 0? Nicholas, do you have a question, buddy? Oh, okay. So I've just put a question in the chat. That's okay. Even though it looks like you've got a defined value there, what is 0 to the 0? It's a pretty big question, right? Maximilian says 1. Abdul Rahman says it's an error. Undefined. So these are all really good questions. Okay. So that's what Maple, we'll get back to that in a minute. That's what Maple thinks of x to the power x. Okay. So the question is, if I wanted to differentiate that function, what does it even look like? Okay, and how do I do it? So let's have a look at how we might do it. Okay, so over here, I used this logarithmic differentiation, right, for the previous example with 6 to the x. Can I do something like that with this? And the answer is yes. Okay, the answer is yes. So I'm going to let y equal that. And I'm only going to do it for, x positive here. I'm not worried about anything else. So based on the previous example, what did I do? Well, I took the natural logarithm of both sides and then I differentiated. Okay, so let's try that again and see if that helps us out. Okay, so I've taken the natural logarithm of both sides, and what I can do if I want to is use the log laws and bring the power to the front. Okay, so what I'm going to do, similar to the previous example, is I'm going to differentiate both sides of the equation with respect to x and use the chain rule. Okay, and the product rule actually. All right, so I can use the product rule here and I can use the chain rule here. All right, so the product rule for this one is going to be something like log x plus x times 1 on x, which is just that. All right, I've applied the chain rule over here, and I have applied the product rule here. Okay, so I want dy dx. I'm going to differentiate this. Sorry, this should be, yeah, I'm going to get dy dx times 1 on y. That. And so now I can rearrange it. And what is y? Y is x to the x. There you go. I'm just missing a d there, aren't I? Okay. I was missing a d there. I was wondering what is 1 on dy? Well, it's dy. Okay, did I do that in the other one? No, I didn't. So d dy. Yep. Okay. So there you go. How neat is that? So the derivative of this is this times the natural logarithm of x plus 1. Wow. Wow. My dog is really impressed. What do you think? What do you think of the derivative? Okay, all right. Sorry. Okay. So this is a really nice approach, as you can see, for differentiating these really difficult exponential functions. Okay. Now, let's go back to the question about 0 to the power 0. Okay. So there was a question about in the chat about 0 to the power 0, and a few people are saying, well, it's undefined and all this sort of stuff. But what we can do, if we want to define it, it's not actually defined for x equals 0. What we can do is just make 0 to the 0 equal to 1 and plug that discontinuity. It's a removable discontinuity. And so you could define 0 to the 0 to be equal to 1. So you're actually defining the value. You're removing the discontinuity. Okay, so that's possible, but it's not included in the domain originally. All right, let's have a look at one more crazy question. Evaluate this monster limit. Okay, so before I do this question, what do you think the limit's going to be? You've got x to the 1 on x as x gets large and positive. Who can have a guess of what they think this is going to be? What is the value of the limit if it exists? Maximilian says 1. Zhonghua says 1. Abdul Rahman says 1. Well, let's have a look at the graph. Du Chun says also 1. Let's have a look at the graph and see if we can understand something. So here is the graph of x to the 1 on x. Now you can see it sort of starts off very small and then goes up, but then it starts coming down. Oh my goodness. And it comes down kind of, I guess kind of slowly. And maybe it might have a horizontal asymptote. Okay. So you can kind of see that, oh, maybe. Okay, so it looks like it's got a horizontal asymptote. Yeah. So that's an interesting question, right? And an interesting comment. 1 on x tends to 0, but the base also gets very large. So there's like a battle, right? There's like a battle going on. So let me show you that. Okay, there's a battle between the base and the exponent. As x gets large and positive, the base is getting large and positive, but the exponent is getting small and positive. Okay, so I think you're right with your suggestions, but how can we show this? What can we do? Well, let me just grab my notes. Where are my notes? Oh yeah. So let me just grab my notes, and I'll show you two ways of doing it. Okay, so let me divide the page into two parts. Yeah, Abdul Rahman, we will use the Hopital's rule, and you're right. It also depends on what x is for the exponent to have a big impact. Okay, so I'll show you two ways of doing it. Okay, so let's write this in the following way. I'm going to write it like this. So it looks a bit messy, but e and natural log are opposite, so I haven't changed anything for this one. Okay, and what I can do is bring the 1 on x to the front, and write it like that. So the 1 on x has come to the front. And so now we've got a constant in the base, and it's just about what happens to this limit. Okay? So this is one way of doing it. Now the limit of that is constant, so you put the limit up there. Okay. So what is this limit going to be? It's going to be infinity over infinity, right? Because log x goes to positive infinity, x goes to positive infinity. So we can use L'Hopital's rule, as Abdul Rahman is saying there. So 1 on x over 1. Okay, here I've just used L'Hopital's rule. So what is this going to be now? The limit is going to be 0. Okay. So the limit, as you correctly predicted, is 1. And here is one way of justifying it. What might be another way? Well, let's use the logarithmic stuff and ideas that we did before. And you can tell me which one you prefer. Okay. Now, we know from L'Hopital's rule that this goes to 0 as x approaches infinity, again by L'Hopital's rule. I won't repeat the thing, right? So what that means is log of 1 goes to 0, a log of y goes to 0 as x goes to infinity. So what will y go to? Y must go to 1. Natural log of y goes to 0 as x goes to positive infinity. So y must go to 1. All right. So what is the value of this, or the limit of this as x goes to infinity? It's got to be 1. Okay. I think the first, for me, the first method of solution is probably the most straightforward, but it's a bit messy. The second one, well, you have to sort of work this out and then work this out. So I don't know. The second one's a bit faster, but yeah, you just have to make a jump here. What do you think? Do you prefer 1 or 2? Let me ask a question. Which method is better? Method 1 or method 2? No. Which one floats your boat? Which one do you think is a magic solution? Lots of people are saying 1. Some people are saying 2. Some people are saying E is a magic number, including you, Steve. It's a bit messy though. Number 1 is a bit messy, but number 2 is all right. Okay. All right. All right, folks, we have 1 minute. Are there any questions? Is there anything you'd like to ask me? What do you think? What would you like to ask? Anyone can turn on their microphone. We don't have many people here right now. We've got 39 students and 1 dog. All right, x to the x. Sure, Carl. Let me go back. Let me go back, buddy. Let me find my slide. X to the x. There you go, Carl. So, Steve, I don't teach Math 1, 2, 3, 1, but I've taught it many times in the past. And in fact, I do have some YouTube videos, like about 200 YouTube videos for that course. So if you want them, I can post a link or do something like that. I'm not sure if you have access though to YouTube where you are. Abdul Rahman asks, why is E considered natural? It's probably just marketing, Abdul Rahman. Bernoulli, who was one of the first people, maybe he wanted to sell it a bit more. I don't know. It comes from French. So yeah, maybe he wanted to sell it a bit more. So I don't know. Some people think it's natural when it's totally unnatural. So I don't know. Yeah, I'm going back, Carl. Don't worry. Well, folks, it's the last Friday lecture. Oh my goodness, for calculus, we have 2 more classes next week for calculus. So we're getting close to the end. And, week 10 is where it's all going to happen. So next week, we will begin the hyperbolic functions. Okay, yeah, the exam's coming, Steve. Are you ready? Are you going to smash that exam? I hope so. So, yeah, you will. I have confidence in you. All right, folks. Well, I will say goodbye. 谢谢 and 再见, and I'll see you next week. Oh, Tom. Well, the product rule is here, Tom. So that's a good question. So the product rule is for this one because it's a product of 2 functions. Yeah, because it's x times log x. And here's the chain rule, Tom. Okay. So, this is the chain rule. And the product rule is just, if you have the derivative of log x, that's 1 on x, and the derivative of x, that's 1. Okay. Oh, hang on. Oh, did I make a mistake? So log x. No, that's correct. That's correct. Okay. All right. Tom, is there anything else you'd like me to talk about? Yeah. All right. All right, everybody. Thank you. See you next week. See you next week. Goodbye. Have a good weekend. And yep, looking forward to it. Bye, everyone.